Welcome, I'm Al Schriesheim. I am the president of the Chicago Council on Science and Technology, and I'd like to welcome everyone this evening to the Physics of Baseball with Dr. Alan Nathan. I am pleased this evening to see all of you here. We have a number of people also on the live stream. And for those of you unfamiliar with the Chicago Council on Science and Technology, we are a nonprofit, and we are dedicated to raising the awareness of the importance of science and technology in our society among the public. And the physics of baseball certainly has societal significance. I'm quite pleased this evening to welcome the members of the board of the Chicago Council on Science and Technology who are here. Let's see, looking around the room, Mary Hendricks. Mary, where? Mary, there you are. Mary Hendricks, who is the president of Lurie Children's Research Center. Kay Torsion, who is president of Torsion Capital Management. Richard La Riviere, who is president of the Field Museum. And last but certainly not least, Bob Arthur, to whom we owe a lot in terms of being able to be here tonight. He's the head of and the key person in Magellan, and you see the Magellan signs all over, and you can thank Bob for getting those of you who wanted to take pictures out on the field tonight and run around the field for that. So I think we should give Bob a hand. Well, tonight's program focuses on the summer pastime, if you will, of the intersection of physics and baseball. It's a wonder, actually. Every time I watch a baseball game on TV, and I'm one of those people who really doesn't watch many baseball games on TV, that the pitcher and the batter actually connect from time to time. It's really amazing. And when you go out in the field and see how far that outfield is from home plate, and consider what it takes to get that ball back from the outfield, even close to home plate, it's really something. Before I start, I so often forget to do this. We are a membership organization, and I would encourage you to take a look at our website, take a look at the programs that we have on that we do, and pick up one of these membership cards at the desk and sign up to be a member. We have a number of very interesting programs coming up. We have one on the 10th of September at the Entrepreneurial Center in Chicago, 1871, on the landscape of innovation. We have another one that should interest all the men in the audience on outs for the sperm count. The mysteries of a declining resource. And that is by Bob Martin, who is at the Field Museum, courtesy of Richard. So, and then we have a program on the technology and tactics of the FBI cybercrime unit. You can't pick up a newspaper today without reading something about cybersecurity and cybercrime. So we do a spectrum of programs that have impact on science and society. Well, I would move right along, and what we have this evening, of course, is a program on how everyone can learn to be a better baseball player by understanding physics. So Alan Nathan spent most of his career as an experimental nuclear physicist and is the Professor Emeritus of Physics at the University of Illinois. He has recently been working on an exciting experiment in Compton scattering at the Thomas Jefferson National Accelerator Laboratory. That is something I actually know something about, since I am the former director of Argonne National Laboratory. Anyway, I think Alan became tired of doing physics and decided to learn something about baseball. So clearly he spends time researching the physics of what is indeed a national pastime. He's written numerous papers on the subject for scientific journals, primarily on the physics of the ball-bat interaction and the flight of the baseball. He's lectured on the subject to scientific and popular audiences, maintains a frequently visited physics of baseball website, baseballphysics.illinois.edu. While his heart, I understand, is in the Boston Red Sox, he has switched his allegiance for the evening to us. So with that, I would like to welcome Professor Alan Evans.
Well, thanks very much for the very kind introduction, Alan. We're both Alans. I sort of kind of dropped out of doing nuclear physics a while ago and decided it was more fun doing baseball physics. And so here I am. I've been doing this really for over maybe a dozen years or so. So as my nuclear physics career has sort of ramped down, this has ramped up, and now I spend virtually all my conscious hours doing these kinds of things. So the title of the talk, The Physics of Baseball, you can observe a lot by watching. That's a famous quote by none other than Yogi Berra, baseball philosopher. And so that is sort of the theme of how I've put this talk together. What I have is a whole set of sort of high-speed, a lot of them high-speed video clips that highlight certain aspects of the physics of baseball that I personally find very illuminating and very interesting. So that's sort of how I've put this talk together. Does anyone recognize who that is? I want to see who it is. All the way in the back. Who is this? Who? No, Prince Fielder bats left-handed, but you have the team right. No, he's also left-handed. And Miguel Cabrera. This is from the World Series last year, and the remarkable thing about this is that notice the bat breaks, and look at that bat continuing to move and vibrating. All right, so let me give you some references. This is how I got started with this. I got started by reading this book, The Physics of Baseball. Professor Bob Adair, who's a bit older than me, but his background is very similar to mine, was a former high-energy physicist and an expert on the physics of baseball. Some very nice quotes from this. Alan, pay attention. Our goal is not to reform the game, but to understand it. So nobody is going to learn how to play the game better by listening to this talk, okay? And quite frankly, I'm living proof that you're not going to get better by listening to this stuff. This is all curiosity-driven kind of research. There are practical aspects to it, but the goal is really to understand, as it is with many areas of science. And here's one of my favorite quotes of his. "The physics of baseball ain't rocket science, it's much harder." And that's really a true statement. So a lot of the things that I've worked on are, follow from pretty much basic physics, but a lot of it is really a lot harder than that. And, one of the things that physicists learn how to do at an early age is to create models for how things behave, do experiments that try to constrain the parameters of those models, then do additional, make predictions and then see how well that works out. It's kind of model building. It's very hard to understand a lot of these things from first principles. So that guides a lot of my own thinking about the subject. There is a much more advanced book. You really have to know a little bit of physics for this book, but it's a more recent book, and it has a lot of the most recent research that's been done in the last decade or so that's not in Adair's book. And my own website that Alan referred to, baseball.physics.illinois.edu, which is, as he said, oft visited, and I visited a lot myself just to keep it up to date. I try to keep the home page of it, interesting and something that's fairly current. Okay, so here is an outline of what I'm going to talk, and these fanciful titles here will become apparent as I go along. So, look, ma, no hands. Nasty, nasty, nasty. 3 for the price of 1. Building a worse mousetrap. Normally engineers try to build a better one. I'm going to talk about building a worse one. And then if I get time, we'll go into extra innings. Okay, look, ma, no hands. So this gets into the heart of the physics of the ball-bat collision. So you can observe a lot by watching, so watch. Here's a ball coming at a steel plate at 120 miles an hour, shot with high-speed video at 30,000 frames per second. And notice that the ball gets really squashed during that collision. The ball maintains contact with the plate about 1,000th of a second. So, and during that time, that ball has to come to a momentary stop and then turn around and go back out again. It's a very violent process. It's a very inefficient process. If you can sort of train your eye on how far the ball advances in one frame, you'll see that before the collision is going about twice as fast as it is after the collision. So it loses about half its speed, which means it loses about 3/4 of its energy. That's very, very inefficient. Here's a picture taken from our hometown newspaper, the Champaign News Gazette, which is a remarkable picture showing the bat and the ball in contact with each other. That's a real photo of opportunity. And notice that the ball flattens out, and it sort of wraps itself around the cylindrical surface of the bat. So this is just a demonstration that the collision is a truly violent collision. So it's no wonder that somebody like myself and Professor Adair, who spent their careers looking at collisions of subatomic particles, might be fascinated by this very similar but really quite different kind of collision. Okay, but despite the fact that these collisions are violent, there are certain laws of physics that have to be obeyed, and one of them is what's known as conservation of momentum. So here is a batter bunting the ball, and what you're supposed to notice is the bat recoils backwards. So what's going on there? The bat has transferred momentum to the ball by turning it around and sending it back out again, and Newton's laws of mechanics say that the ball has to transfer an equal and opposite momentum to the bat that makes the bat recoil backwards. Same effect that you get when you're firing a rifle. The